So why do we want to use limits at all? Okay. Well, because the limits describe the behavior around a point, not necessarily at the point itself. Not necessarily what the function is doing at the point itself. So here are 3 examples where we get different information in each case. Okay. So for this one here, let's look at the graph of f. Here I'm asking you to determine what is f of 4. We're just going to do this graphically here. What is f of 4? Yeah, f of 4 is -3. Okay. How do I do that? Well, I look at saying, when I plug in 4 into the function, what is the corresponding y value? The corresponding y value is -3. Okay. Now, this next step is a completely different step. I want to look at the behavior of the function near x equals 4. Okay. So I'm going to take x values, like maybe this x value right there. If I take that x value right there, that corresponds to this point right here on the graph, right? Which corresponds to what y value? This y value right there. Then if I take a different x value, like maybe this one right here, that corresponds to this point on the graph, which corresponds to that y value. And if we do one more, if I take, say, that x value right there, that would correspond to that point right there, which would correspond to that y value right there, as best I can draw on this tiny little picture. Okay? That was coming from one direction. Okay? What if we came from the other direction and we picked, I don't know, maybe this x value right there? This x value corresponds to that y value, right? Let me make that an arrow, not a point. That x value corresponds to that y value, to this point on the graph, which corresponds to that particular f of x value, right? And then we take another one. We bring that in closer, maybe right there. Okay. Well, that would be that y value. Okay. And then if we took one even closer, I don't know, maybe that one right there, that corresponds to that point, which corresponds to that y value. What are we seeing? As the x values get closer and closer to 4, the y values are getting closer and closer to what number? -3 again. So in this case, the functional value and the limit value agreed with each other. To be honest, one way of looking at it is, by evaluating the limit, we didn't really get any new information. That's because this is a very well-behaved function, and I'm going to start using some vocabulary that we're going to define later. This is what's called a continuous function. When you have continuous functions, looking at the limits of continuous functions isn't very exciting. Limits are exciting when you're dealing with discontinuous functions. All right, so the next thing I want to introduce is the notion of left and right hand limits. Okay? So, this definition looks very similar to our definition of the limit, what I'm going to sometimes call the limit proper, the limit definition that I gave before. So for a function defined on some open interval of the form a comma c, okay, if as x approaches c from the left, the range values approach some value L, then we're going to write the limit as x approaches c from the left of f of x is equal to L. This is the same idea as before. We're saying as the x values get closer and closer to some number, in this case I'm calling it c, if as x gets closer and closer to c, the y values get closer and closer to L, then we'll make this limit statement. What's the difference? We are only approaching c from one direction. What direction? From the left. Okay. How do I denote that we're approaching from the left? I put a little minus sign up there. That means we're coming from the left. Now, this is very important, folks. The direction of approach is from the left. The value that we're approaching then will be to the right of where we're approaching from. Okay? Left and right is always a matter of relative position, right? So I'm saying the direction of approach is from the left. Okay, so a lot of times people get those confused. They switch them up. Okay? The direction of approach is coming from the left. So this is read, the limit as x approaches c from the left of f of x is L. In this case, we would call L the left-hand limit of this function. Okay? So let's go ahead and denote that graphically. Okay? Here's the value c that we're approaching. Okay? So if we take x values, let's say we take this x value right here. That corresponds to that point on the graph up here, which corresponds to this y value right here. Now let's say we pick another x value. Let's go a little bit closer. Let's pick this x value right here. Okay? That corresponds to this point on the graph right here, right? Which corresponds to this y value right here. Now let's go closer. Let's go to here. Okay? That gives us this point right here, which gives us this y value right here. And as we get even closer, what does it seem that our y values are approaching? They're getting closer and closer to whom? To L. Okay? Now, we only picked what type of x values? X values that were where? X values that were to the left of c. So how do we denote this picture? We would write the limit as x approaches c from the left of f of x is equal to L. So let's practice reading this aloud. This says the limit as x approaches c from the left of f of x is L. So in these problems, I think it's very important to always be thinking of domain and range. Okay? As the domain values get closer to c, but specifically coming from the left of c, the y values get closer to L. All right.